Good morning, everybody. We are continuing with Lecture 5 on the Statistical Computing and Machine Learning course. This is Nicholas Zabaras. So today we will discuss about the multivariate Gaussian. And of course, we will need more than one lecture to cover the linear algebra involved with the multivariate Gaussian, but at least today you will see how the distribution looks like. We will discuss about the multivariate student's t distribution. Effectively, we will see how to extend the univariate student's t distribution to a multivariate context. And then we will talk a little bit about the Dirichlet distribution that is going to be very important, especially on classification problems. Okay, so the lecture today will involve the review of the multivariate Gaussian in some basic way and of student's t distribution. And we will finish with the Dirichlet distribution. So this is going to be a short lecture, but the topics involve a little bit more algebra and they are a little bit more advanced than the earlier distributions we have seen up to now. So what are the goals for today's lecture? First, I want you to familiarize yourselves with the multivariate Gaussian and student's t. Both of them will be essential for this course. We need to learn about the Dirichlet distribution and some of the algebra also involved with the Dirichlet distribution that we will take advantage in subsequent lectures in this course. Okay, so let me just write down the first, the references are the same as in the earlier introductory lecture, so I'm not going to bother with that. But let me start with the univariate Gaussian. So we have a variable x that follows a Gaussian with mean x0 and variance sigma squared. So I remind you how that looks like. So this is the probability that x is less or equal to t. So our PDF is, of course, this normalizing factor times this exponential. And so what we're going to do is we're going to extend this to a multivariate context. And I'm going to give you directly the formula that gives the PDF for a multivariate Gaussian. Things in some sense look similar in the exponential. Of course, the sigma squared here has become the 1 over sigma squared has become this covariance matrix inverse, and this square in x minus x0 has now become x minus x0 transpose x minus x0 because remember that x and x0 in our case are vectors. Now, similarly, this sigma square that you see here has now become the determinant of the covariance matrix. And I remind you that the covariance matrix is a symmetric, semi-positive definite. Most of the cases we will consider it will be positive definite as it is listed here. Now, I already mentioned in an earlier lecture that the fact that sigma is symmetric has a lot of implications, because if x is a very high dimensional random vector, so if d is very high, you will need d square elements to prescribe to define the metric sigma, but if sigma is symmetric, we will actually need d by d plus 1 over 2 elements to do so. Now, with that said, and with the symmetry property for sigma, notice that this exponential here is not being affected by the symmetry process, by the symmetry property of sigma. Okay, so we could have any sort of metric sigma here, and then this will be equivalent if we use the symmetric part of that sigma. Okay, somehow just remember that this quadratic form is not being affected by the symmetry property of the covariance matrix. Okay, let me just give you without proof a simple transformation rule for Gaussians. So if you define these matrices A and B, of dimensions m times d and a vector c in Rm, you can actually show that if x1 and x2 are Gaussians and they are independent Gaussians, then if you take the linear combination of those, ax1 plus bx2 plus c, then it turns out to also be a Gaussian with the mean that you see here. And then the covariance matrix is a sigma 1 a transpose plus b sigma 2 b transpose. Now, I mean, in some sense, we have seen a lot of the pieces. We have seen these individual pieces when we talk about linear transformations, if you remember, in the earlier lecture. And also we have seen this addition of the covariances that you see here that are, is valid when x1 and x2 are independent random variables. So this would be useful properties when you do calculations with Gaussians. So please keep those handy to use them when you need them. All right, so I'm giving you some plots and a little MATLAB program to play and understand more the multivariate Gaussian in 2 dimensions. So here what you see on this plot, you see contours, equal probability contours of the joint distribution of x and y. You get these ellipses. If you take a particular value of y, so here is y equal 2, I am plotting the conditional distribution of p of x given y that you see here. And also on the plot on the bottom, what I'm actually doing is I'm also plotting the marginal distribution p of x. All right, so you should be able, when you have a multivariate Gaussian, to be able to go to the conditional distributions and also to the marginal distributions with no difficulties, and also you should be able to do plots like this. So again, these are the 3-dimensional version. So rather than using contours of the joint distribution, I am plotting this probability density in 3 dimensions. And again, you can see if you take a slice at y equal to 2, this is the conditional distribution that I'm plotting on the left side as well. And similarly here, you have the marginal p of x, but the whole plot is given in a more nice fashion in 3 dimensions. Okay, so certainly do play with this type of plots, because you will need to be able to present your results using similar plots in 2 dimensions at least. Okay, so we're going to come back to the multivariate Gaussian. There is a lot of linear algebra that somebody can do and a lot of different types of factorizations. For example, I haven't really said for a d-dimensional multivariate Gaussian how you compute the marginals or how you compute the conditionals, and for example, how do you go from p of x and y to p of x given y, or to p of y given x, or to p of x or to p of y. So we will see these transformations later on in the course, because we will need them for Bayesian analysis. But right now, just keep in mind the big definition of the multivariate Gaussian that we gave in the previous slides, and that should be sufficient for allowing us to proceed. So now what I'm going to do, I am going to introduce the multivariate student state distribution, and of course our first starting point is this fundamental equation that you see on the top. And I remind you what this equation is all about, that we stated that the student t distribution is really the average of Gaussians for precisions that are being sampled from a gamma distribution. So if you take all of these Gaussians for all of these taus sampled from this gamma distribution, and you marginalize tau out, right? So you sum over all possible taus, then the distribution that comes out of this is a student t distribution. So obviously our approach to define a multivariate student t distribution is somehow to use the multivariate Gaussian here and somehow average the variance, the covariance, with some gamma distributions. Of course, the gamma distribution is for scalar variables, right? So you remember tau is positive, is a scalar variable. So if I have a matrix here, I will not be able to actually use the gamma distribution to do this averaging. Is not going to work. So what actually we will do is we are going to try to rewrite this equation where somehow we're going to write the covariance matrix as some scalar times a matrix where the matrix is going to be fixed, and that scalar is the one that we're going to sample from the gamma distribution. So somehow we are going to be able to do this integration in a scalar variable, but produce a student t distribution that is multivariate. Okay, so so how can we do this? Let me go directly to the equation. So this is our gamma distribution, and we're going to write the multivariate student distribution as the result of the following integral. I'm running a little bit ahead of myself. So this is actually a reparametrization of the equation that you see on the top, and in preparation for doing the multivariate version of this equation. And the only thing that I have done to the equation on the top is, instead of a, I use nu over 2, and I have defined the ratio a over b to be lambda, and I have defined tau to be eta times a over b. All right, so tau is eta times lambda. So if you substitute those things in the equation on the top, you get a new parameterization for the univariate student t distribution, where you have eta times lambda here. A becomes nu over 2, and b also becomes nu over 2. Okay, so notice that lambda here is not part of the integral anymore. All right, this is a key ingredient in this equation. So lambda is not coming anywhere in the integral. What is coming is this scalar parameter eta. All right, this is what we average with, right, and this is what we integrate out. So now we can really extend this to the multivariate case, where instead of a scalar precision lambda, what we're going to do is we're going to put a precision matrix lambda, all right, but the integration is still going to be in this parameter eta that is scalar. So let me just write that equation, the way it's going to look like. So this equation is going to look like that. Okay, so you notice instead of using a univariate Gaussian, now I have the multivariate Gaussian with mean mu and precision eta times lambda, and the averaging is happening with respect to the parameter eta. Okay, so we're able basically with an integration of the parameter eta to produce a multivariate student t distribution. So we keep the matrix lambda fixed, but we allow eta to be sampled from this gamma distribution, and that's what we integrate out. Okay, so the idea again is rather simple. We started with our definition of the univariate student t distribution. We did a simple parameterization to bring it in a form where somehow the precision is separated, multiplied with some scalar eta, and these are the new variables that we introduce. So really nothing but redefinition of the variables. And the only thing I'm going to say, since we already covered the topic of change of variables, remember here you have a gamma distribution for tau, and here you have a gamma distribution for eta, and tau is eta times a over b, and a over b is lambda. Okay, so remember that again you are changing a PDF from tau to a PDF from eta, and of course you are changing the integration as well from an integration from tau to eta. So in some sense this times that is equal to this times that, but if you feel like, you can look at the formulas on how you transform this PDF to this PDF, and then do change of variables in the integration, and you will get the same answer. Just be cautious again when you do change of variables for PDFs. And we concluded again with this equation on the bottom that only involves scalar integration in eta, and I stated that the result of this is what we're going to call the multivariate Gaussian, which is an infinite mixture, if you like, of multivariate Gaussians with precisions, integrated out in the fashion that I indicate with this formula. All right, so how do we do now this integration in eta? I am not going to bother to go through all the algebra. It's actually straightforward because the integration is in some parameter, some scalar parameter eta. So if you do that integration, you actually get the result that you see here, and this is the student t distribution for a vector setting. Everything should look familiar. This is the gamma functions, this is the determinant of the precision metrics, and delta square, just to save me space, is what you see here. Right? You remember here we usually have the inverse of the variance, but now we have the precision lambda of the student t distribution. So this entity here is what is called the Mahalanobis distance, and it is actually extremely important quantity that comes all the time in calculations. So just remember the definition. What you do get here is the Mahalanobis distance, okay? You will actually get the same thing in the exponential of a multivariate Gaussian, so I could have introduced this earlier, but right now I have it in the context of the student's t distribution. Again, how this derivation comes, how this integral gives me this nice form, I am not going to bother you. Here is the derivation. Effectively, if you do some extra transformation of variables, okay, if I go from eta to this new variable tau, not related with what we had before, just put all things together, what you actually do get is you get an integral that is actually directly computed in terms of the gamma function. It is the gamma function itself evaluated at the argument that you see here, and that's how, with two lines calculation, we do get the student t distribution. Obviously, because both these Gaussians and the gamma distribution were normalized, you do expect that this distribution is normalized. So all of these things that you see on the front are effectively take care of the normalization of the student t distribution. So if you integrate this, right, so you will actually, from minus infinity to infinity, you will get the integral to be equal to 1. Okay. So let me give you some of the standard results for the student t distribution. Similarly to the univariate case, when the degrees of freedom are only greater than 1, you can define the expectation. For nu equal to 1, you cannot, because the heavy tails make the integral that defines the expectation to be undefined. For nu greater than 2, this is the covariance given by this nice form, and the mode coincides the same way as for the Gaussian, coincides with the expectation of the distribution. Now, I do not want to have to do all the algebra here, okay? Some of the proofs are actually given in this slide. So, for example, if you want to get the expectation, I am doing a transformation of variables. I substitute x to be z plus mu. All right, it's going to simplify the algebra, and the integral, the first integral that multiplies z by this term is going to be 0 because this is an odd function, this is an even function, and the other integral, the mu, will come outside, and everything else will be actually the student t distribution that when you integrate in z gives you 1 because of the normalization. So immediately you actually see that the expectation of v of x is equal to mu, all right? So actually just sort of a trivial statement, just this transformation alone is sufficient to give you the required answer. Now the covariance is a little bit more involved, nothing fancy, all right? So again, I am going to give you the equations for you to follow at home this algebra, and again, the integrations that you do have to perform at the end of the day involve basically integrations in a scalar, so that you should not have any problem, and many of these integrals give you gamma functions as a result, and the answer comes to be a very nice quantity here that you see, right? And remember, it is only defined if nu greater than 2. Okay, now someone may ask, now you remember this nice property that we concluded for the univariate Gaussian? We saw that when the degrees of freedom of nu of the univariate Gaussian goes to infinity, then this distribution converges to a Gaussian with mean mu and precision lambda. So the question will be, do we have the same property for the multivariate student t the way that we have defined it? And the answer is absolutely yes. And the proof is actually given on the slide here. And there is really nothing fancy. It's actually identical more or less to the univariate case. So what you need to do is take this term that you see here at the end of the PDF and write it as the exponential of minus this coefficient times the log of 1 plus delta square over v, okay? And here we have the log of 1 plus a small number. It's a small number because we're interested for nu going to infinity, and log of 1 plus small number, if you do a Taylor series expansion, the first leading term is that small number, so delta square over nu. So nu and nu cancel out on the leading term, and then you get the exponential that corresponds to the Gaussian. And you remember delta is the Mahalanobis distance that also comes to be part of that exponential in the Gaussian. So, in conclusion, the multivariate Gaussian does, the multivariate student t does become a Gaussian as the degrees of freedom nu go to infinity. So if you have nu going to infinity, or it's a very large number, actually with very good confidence you can do your approximations using a Gaussian instead, because that may lead to algebra that it is simpler. Now, usually I remind you that in practice, when this distribution is used, people take the degrees of freedom to be about equal to 4, and in that case still nu is not large enough to approximate it with a Gaussian unless you have to, okay? But again, this is a nice property that gives you a sense of this multivariate student t, and also gives you a sense why we call this matrix lambda to be the precision of the student t distribution. It is the precision because only asymptotically it turns out to be the precision of the multivariate Gaussian, but the precision, you can see here the covariance of x is not lambda inverse, is lambda inverse times this coefficient. So do not confuse, right, lambda with the precision of the multivariate student t, but you notice this coefficient becomes 1 when nu goes to infinity. All right, let me just say something. If you go and check different books or even if you look at Wikipedia, you can see that often the student t-distribution is written not using lambda, but using the inverse of lambda, which is a covariance measure. So please pay attention when you use this type of distributions, because the parametrization may be a little bit different from the one that we use in this class. So in some books or in the web, you will find parametrization in terms of sigma, which is the inverse of lambda, but there is a number of key publications that actually not only they don't use lambda or sigma, they use the degrees of freedom times this matrix sigma. Okay, so always pay attention what it is that the parameters of the distribution that you're seeing represents. And again, I remind you, we're interested on the student's t-distribution because of the heavy tails, and I remind you the heavy tails have implications to the fact that the distribution turns out to be robust to outliers. And I know we haven't done explicitly things like the maximum likelihood estimation for this type of distributions, because the algebra is a little bit complex. But I gave you some plots for the univariate case, and the same type of conclusions are also true for the multivariate case. Okay, so we are done with the student's t-distribution. So what I want to do now is I want to move to another distribution, which is going to be a little bit more complex to understand it. But I think when we start using it in applications, it will make a lot of sense. So for now, I want to start giving you the definition and also some of the properties of the Dirichlet distribution. So let me remind you the multinomial distribution. If you remember, we had a coin that has k different faces or k different states. So we are conducting n experiments, capital N experiments, and in the multinomial setting, we get m1 times the state 1, m2 times the state 2, and m subscript capital N the state n. So the Dirichlet distribution is going to come to be what we're going to call a prior distribution when we do Bayesian analysis for the probabilities mu1, mu2, mu subscript n that we have seen in the multinomial distribution. So remember, the multinomial distribution was proportional. Basically, the PDF was proportional to mu1 to a power m1, mu2 to a power m2, mu m to a power mu n. So the Dirichlet distribution is what is called a conjugate prior, has very similar form to the multinomial distribution, and it looks like this. All right. So instead, in the multinomial distribution, the powers that we had here, they were mu m, mu1, mu2, mu3, mu n for the different k's from 1 to capital K. Okay. So before, I think I said mu1, mu2 it has supposed to be a mu capital K, right? So capital K is the number of states that we have in our problem. So this Dirichlet distribution is a probability over this vector mu, has this form, and the parameters of the distribution are these coefficients alpha k. Obviously the same as in the multinomial distribution, the sum of these probabilities has to be equal to 1, right? So when you do an experiment with this coin, you're gonna, at each time, you're gonna be in one of those k states. So the sum of the probabilities on being on each state has to give you 1. So mu k's between 0 and 1, sum equal to 1, and this is my Dirichlet distribution. So notice, because we have this constraint, even though this appears to be sort of, if I can say, capital K type of dimensional distribution, in reality, because the number of independent variables are K minus 1, right? Because of this constraint, the distribution is defined in the K-dimensional space rather than in the capital K space. Okay? So effectively, you can take, for example, mu capital K and write it as 1 minus mu1 minus mu2 minus etc. minus mu subscript capital K minus 1, right? So it is a distribution in the K minus 1 dimensional space. Okay? If you want to see how the normalization factor looks like for the Dirichlet distribution, I am giving it in the equation that you see on this slide. There is the beta function that is involved in normalizing the Dirichlet distribution, and for those who forgot, I give you the definition of the beta function. So the beta function is the product of the gamma functions computed in each of these coefficients a1, a2, etc., and divided by the gamma function on the summation of these coefficients. Okay? Just an indication of how we're going to plot these distributions, at least in 3 dimensions. So in 3 dimensions, the Dirichlet distribution is going to be a distribution over the vector mu1, mu2, mu3, and because mu1 and mu2 and mu3 has to be equal to 1, really the Dirichlet distribution is going to be confined on this plane that you see here with these blue lines. So later on, when I plot for different values of alpha the Dirichlet distribution, you will see it defined on the plane that you see in this figure on the bottom of this slide. Okay. So this is our definition, right? And you have to trust me that there is lots of value to the Dirichlet distribution, both from an educational point of view, but more importantly for research. There are extensions of the Dirichlet distribution, and if you search on Wikipedia, you will also see what is also defined as a Dirichlet process, and I don't think that's a topic we will cover in this course, but right now we will limit ourselves with this Dirichlet distribution defined over these probabilities mu, and these probability mu's, I want you to think always of the probabilities that are introduced in the multinomial distribution we saw 1 or 2 lectures ago. Okay, so let me start doing some algebra with the Dirichlet distribution, and I'm not going to give you all the details, but I'm going to try to highlight enough details so when you go home you can actually read those slides and being able to reproduce these derivations on your own. Remember, this course is not about doing integrals or derivations, but also with that said, I don't want you to think that things come out of nowhere. There is very simple algebra that leads to every result and every equation that you will see in this course, and being able to actually remove the magic and knowing how to do that algebra may be an essential element for your education and the type of research you'll be doing tomorrow. All right, so let me rewrite the Dirichlet distribution the way that you see here. And you remember we had 1 over the beta function, and I wrote it explicitly now in terms of this coefficient. So this is 1 of the beta function, and this is the definition that I had before. Remember, A0 is the sum of all the coefficients, and A1, AK are the coefficients that define the Dirichlet distribution. So let me give you one of the results that is going to be very useful when we start doing algebra that involves the Dirichlet distribution. And this result is going to involve the expectation of the log of mu j from j1 to capital K. So I need to derive an equation that will give us the expectation of the log of mu j. Okay, so to do that, let me introduce this equation that you see here in yellow, and I will explain what that equation is, because I'm going to try to use this equation in a derivation to come. So what is this derivation? Is the derivative with respect to the alpha j of this product term. So I'm not taking derivatives yet of k of a, all right? So I'm taking derivatives of this product in my PDF with respect to one of the coefficients alpha j. So alpha j can be 1, 2, or capital K, so I won't take the derivatives of one of those. So to take the derivatives easily, I am writing this mu to the alpha k minus 1 as the exponential of alpha k minus 1 log of mu k, and then you have a product of this from k1 to capital K. Only one of these terms have an alpha j on it. So if you have you know, all the remaining exponentials will remain as is, and the term that involves alpha j is going to give us, when you take derivatives, it will give us log of mj times the same term, which will be mu j to alpha j minus 1. So effectively, when you take derivatives with respect to alpha j, you will get log of mj, right, times the product that you started with. Okay, you can again look and spend a few seconds if you have any questions, or you can come and ask me about this. But the derivative with respect to alpha j is log of mu j times this product. So let's do the derivation that I mentioned before, which is the expectation of log of mu j. So to use the log of mu j, the expectation, I'm going to have log of mu j, and here I'm going to have times my Dirichlet PDF, all right, integrated over mu1, mu2, mu subscript capital K. And you notice I split it, the integrals, because, you know, obviously I'm going to do something special. There is mu j here, and then I have all the other k's from 1 to capital K. So I will need to be careful on how I only compute the expectation of log of mu j. Okay? So let's follow the algebra a little bit. Okay? So I have the expectation of this, nice. So k of a is outside the integral, does not involve any of the mu's. And here I have log of mu j times this product. Now you can see why I did the calculation that's given in the yellow box, because the log of mu j times this whole product is the derivative with respect to aj of the product. Okay, is the derivative with respect to the aj with respect to the whole product. So I can remove the differentiation outside the integral, all right? So I can put del over del h of this whole integral. And now you look at this term, right? What is it, if you think about it, all right? So if you remember that my PDF is k times this. So if you integrate this over all possible values of the mu's, and every mu varies from 0 to 1, this integration is supposed to give me 1 because of normalization constraint. So the integral of this product times k of a will be equal to 1. So the integral of this product will be 1 over k. And this is exactly what I have here, right? This whole integral from the normalization of the Dirichlet distribution gives me 1 over k. So I have k times the derivative with respect to aj of 1 over k, and you can see with little tricks of taking derivatives with respect to log, this is minus the derivative of the log of k with respect to aj. And I remind you what k of a is by definition, all right? So you notice the when you take logs of Ka, you're going to get log of gamma of A0 minus the summation of the logs of all of these Aj's on the bottom, right? So when you take derivatives with respect to the Aj, you're going to get one contribution from the term in the numerator, and then only one contribution from the term gamma of Aj. The rest of the terms, once you take logs, right, they will not give you any contribution. They don't depend on Aj. So what you get is, you get this very nice result that the expectation of log of mu j is the derivative of log of gamma of Aj with respect to Aj minus the derivative of gamma computed at A0 with respect to A0. Okay? By the way, when you take derivatives, you're going to have to take derivatives of this with respect to Aj, right? So the derivative with respect to Aj will be first the derivative with respect to A0, which is what I have here, and then the derivative of A0 with respect to Aj, which is 1. That's why you have a derivative here with respect to A0. So this function that you see in here, which is the log of the gamma function with respect to its argument, is called the di-gamma function. And I know you have not seen this before, but it is actually a function that is going to come to be useful. This derivation is something we're going to use in machine learning. Immediately my mind goes to calculations in the context of variational methods, but I am sure this same calculation comes elsewhere as well. So the calculation, you can write it in simple form as the expectation of log of mu j equal psi of Aj minus psi of A0, where these psi's are the derivatives with respect to the argument of gamma functions. Okay? So we have derivatives with respect to the arguments of the logs of gamma functions. And this calculation gives me the expectation of the log of mu j for j equal 1 to capital K. Right? So I can use this for any of my mu j's. So just remember this formula. If it comes, you look back at it and you say, now I understand why we use it, but for now it's just another homework problem with algebra that looks useless unless actually we can use it somewhere in real machine learning calculations. Okay, let me pose now the following question. Okay, so we have this Dirichlet distribution, looks like nicely like that, all right? And somebody will say, I don't really believe you that this weird term with the ratio of these gamma functions is actually the correct normalizing factor. How this result comes, what algebra did I do to actually get this result? So we have the derivation actually for the normalization factor, and again, I don't want to go through all the algebra because it will it's something that is not really essential for this course, but I know for those who like to know things and know where things come from, you may want to follow the derivation that I'm giving on this in the next slide. So let me just highlight it, and I'm going to tell you how it works. Okay, so the first thing I'm going to do is I am going to write the Dirichlet PDF using only independent arguments. So I am going to get rid actually of mu. So if I can go back, right? So using this notation with capital K, so I am going to get rid of mu subscript capital K and write it as 1 minus mu1 minus mu2 minus mu subscript K minus 1. So when I have a distribution defined in K dimensions, right, I'm only going to use K minus 1 arguments for that distribution. So what I'm going to do is I'm going to write the distribution in m dimensions, right, using m minus 1 terms. And the mth term that you see here, all right, I am writing it as 1 minus the summation of the previous m minus 1 mu's to the power a subscript m minus 1. Okay, now why did I change the notation from capital K to capital M? Because actually I'm going to try to use induction to prove the normalization formula that we had in the previous slide. So I am going to actually assume that if I have a distribution in m minus 1 dimension that is normalized with the formula that we have seen before, then this distribution that you see here in m dimensions will also be normalized. Now, you may ask, well, when you do induction, you also have to show the case for, m equal to 2, right? Just to make life easy, for m equal to 2. And you may actually ask the question here, what distribution, what PDF does the Dirichlet distribution looks like if you take m equal to 2, right? So if you take actually m equal to 2, you're going to have only one term mu to some power alpha minus 1, and then you're going to have another term 1 minus mu to another power minus 1. And you know what that distribution is? That's the beta distribution. And you can solve from the normalization of the beta distribution that we did that if you try to use induction for m equal to, the Dirichlet distribution is normalized. So the calculation we're going to do is we're going to try to prove that the distribution is normalized in m dimensions if it is normalized in m minus 1 dimensions. So this is the distribution in m dimensions, but remember the trick I did here, I got rid of the depending term. I wrote mu subscript m as 1 minus all the previous mu's. Okay, so I am not going to do the algebra, but let me just say, so this is, you write this equation for the distribution with m terms, right? So what we're going to do is we're going to integrate mu subscript m minus 1 to make this distribution actually to become a Dirichlet distribution in the m minus 1 dimensional space, which we know it's normalized, and from the normalization in m minus 1 dimensions, we're going to be able to say something about what this coefficient Cm is, and it's going to turn out that Cm is the normalization coefficient that we saw before for m dimensions. Again, I am not going to do the algebra. I think I tried to highlight it. Two ingredients, right? We're going to prove that this is normalized properly, so we're going to derive this in terms of the gamma functions that we had before. And the way we're going to do that is by assuming that the Dirichlet distribution is normalized for m minus 1 terms. So to get the distribution for m minus 1 terms, what I can do is integrate mu m minus 1 out, and the distribution that I will get will only have m minus 2 independent terms, and that distribution will be normalized by assumption from my induction argument. And if I use the correct form for the normalized distribution with total m minus 1 term, including the dependent term, then you can evaluate what Cm is, and that will complete the derivation using induction. So again, if you integrate mu minus 1 out, there is really nothing but simple integration with only one change of variables that I indicate here. So if you do the calculations, you do get a nice integral that is actually immediately easy to calculate, because this is the normalization of the beta distribution, the beta PDF given by this ratio of the gamma functions. So now you know that Cm times this, right? We're going to have to come to prove that they are going to give us the correct normalization term for the m-dimensional Dirichlet distribution. But if you pay close attention, here I have m minus 2 term, and then I have another dependent term. So I really have a Dirichlet distribution in m minus 1 dimensions. So Cm times all of these gamma factors that came from the integration have to be the normalization constant for a Dirichlet distribution in m minus 1 dimensions. And we know that is what it is from induction, right? And so when you substitute that, right, what you assume to be true for m minus 1 terms, and you solve for Cm, you do get the required answer that you see on the bottom. Okay, lots of algebra, but actually, if you follow the calculations, these 2 slides and what you see there is all that you need, and the rest, as they say, is complicated looking equations, but the final answer is extremely essential for normalizing the Dirichlet distribution. And actually, maybe somebody can ask me, do we really care about this normalization of these distributions? Because it seems in most of our examples, these normalization constants look very complicated. So when we do sampling from different distributions, we will actually, in most of the examples we will do, we don't really need to care much about the normalization constants. But there is one topic that is essential to this course, where these normalization constants come to be very important, and that has to do with the idea of Bayesian model selection. And you will see that everything in Bayesian model selection involves the normalization constants. So you will need to actually be familiar with these normalization constants. You will need to know where they come, and actually, in some sense, you will need to be able to do some sort of optimization with these normalization constants, because if I said they're being used for model selection, so somehow if you're going to do model selection, find the best model, that tells me you're going to have to optimize something that maybe involves these normalization constants, and derivatives for optimization may be a very useful type of calculation for at least gradient-based type of optimization methods. So for now, there are formulas for normalization, but they are extremely important, and they will be used in this course. Otherwise, I will not be taking the effort to actually review this type of things. So let me, I mentioned before that the Dirichlet distribution is used as a prior for the mu's that come in the multinomial distribution, and I know the concept of priors and posteriors will come up in a lecture very soon, so to do this rigorously, but I can start throwing ideas at you now, right? We already have, you remember, if you do a number of n experiments with the multinomial distribution, and you collect m1 times representing the number that you hit state 1, m2 the number of times that you hit state 2, etc. This is the likelihood coming from the multinomial distribution. So I already mentioned that the Dirichlet is the appropriate prior. It's a conjugate prior to this likelihood because it has sort of the same mathematical form. And what does that mean? It has the same mathematical form. It means that if you're going to compute the posterior of mu given your data, this is what I call a posterior distribution. The posterior of mu given the data, that is, from Bayes' rule, is proportional to the likelihood times the prior. And if the likelihood looks like that, and my prior has the same form but with coefficients alpha k minus 1, you can see that the posterior has the same form as the likelihood, but instead of mk in the powers, I have alpha k minus 1. Okay, so if you want me to write this explicitly, the posterior becomes also a Dirichlet distribution with coefficients alpha 1 plus m1, alpha k plus mk. And actually you can start even putting some physical meaning to what alpha 1, alpha k imply, because if m1, mk is the number of times that in my experiments I hit state 1 and the number of times I hit state capital K, you can think as alpha 1 as the pseudo number of the times that I hit state 1 if you sort of try to interpret your prior as representing some pseudo experiments. Okay, so you can actually see that the prior is like bringing to the posterior some alpha 1 times of pseudo counts of hitting state 1 and alpha capital K number of times of hitting state K. Okay, so this is very important and it's very typical for this type of distributions, and we will formally expand on this idea in this course once we introduce the details of Bayesian analysis. Alright, so if you want to explicitly write this distribution with its full normalization, so the posterior of mu is given by this nice expression that you see on the bottom, and again it's a Dirichlet distribution with parameters alpha k plus mu k. Alright, so I'm practically done, so the only thing I want to do with this lecture is to give you a few pictures, and so let me give you a few pictures of the Dirichlet distribution in in 3 dimensions. Alright, so what you see here is, you remember I mentioned that we're going to have to plot this distribution on the plane. And the plane here, I'm only showing it in 2 dimensions. Okay, so on the picture on the left, you see the Dirichlet distribution where all the parameters are 1. So if the Dirichlet distribution has all the parameters 1, this is a uniform distribution. You remember every term looks mu to the power alpha minus 1. So if alpha equal to 1, you basically get the uniform distribution. If the parameters are all 2, you get a broad but centered distribution. That's where the probability mass is, and in this case the center is at the location 1/3, 1/3, 1/3. As the parameters are, we keep them equal, but the numbers increase. The distribution becomes more narrow, centered at this location. So in some sense, this parameter A0, that is the sum of all the alphas, defines how big the distribution is. And we can see some distributions that they are not centered, but they're in the corners of my triangular. And you can see here, I am on this corner by using a higher value for A2. I am on this corner by using a higher value of A2. And if you want a distribution that sort of puts most of its mass on the boundary, and this can be very important. So here we had most of the mass in the center. So if you want to put most of the mass in the boundary, you can use a distribution where all the coefficients are equal but less than 1. All right. So if you have a distribution with the coefficients being less than 1, here is 0.9, you can see much of the probability mass is on the boundary. All right, similar plots here for different values. So here all the values are equal to 0.1, and the plots are in 3D. Here all the values are equal to 10. This should actually be, I suppose, little k, right? So I'm taking all the values to be equal to 10, and this is all my values ak to be equal to 1. So this capital K should be little k, and I will correct it on the post-it slides. A few more plots. Again, these plots are coming from the PMTK MATLAB toolbox from Kevin Murphy's machine learning book, so you can play with those. And again, the same type of plots in 2 dimensions or in 3 dimensions. And then I'm going to finish actually with a few samples drawn from the Dirichlet distribution in 5 dimensions. So you can see here this for samples that they are all 5s, I mean for parameters, I'm sorry, that they're all 5s. You get these samples that look like that, all right? And if you take all the alphas to be 0.1, then you remember what I mentioned before, right? That most of the probability mass is in the edges of the distribution, and that's why you can see, I mean, here I only have a few samples, but you can see lots of the samples are concentrated on the 2 edges of this distribution. All right, so let me stop there, and we will start moving to a few things beyond reviewing PDFs. I think we have enough PDFs covered to keep us going. So I will start discussing a little bit about the central limit theorem, and also sort of give you some primitive ideas on Monte Carlo methods derived basically from the central limit theorem, and then we will do some examples. All right, so until the next time, please study these slides, and do let me know if you have any questions. Thank you.